Welcome. We are here today to discuss the Neuroevolution book, and in particular, why we wrote it and what's so cool about it and how you can get involved in this area. So let's start with what's different about Neuroevolution compared to other machine learning techniques. What do you guys think?
Yeah, I think at Neuroevolution it can be more creative than typically deep learning approaches. Like it can come up with solutions that we might not have thought about, and then it's often applied to controlling agents instead of just like a supervised learning task. And I think that makes it exciting, and it can come up with creative discoveries that the designer might not have even thought about it.
I thought when I started learning about neuroevolution or evolutionary algorithms in general, I just thought they're just very useful general purpose algorithms. Like when we're working on machine learning and deep learning, you kind of have to be very specific about what you're optimizing for. But for evolution, it's very general purpose. Sebastian said you can have so many different agents, so many different problems. And actually, these algorithms could be very creative of discovering things that the researchers themselves did not expect. So I think it's a very exciting area.
Yeah, for me, I think that one of the coolest things about Neuroevolution is that I like Charlie Munger's things. One of his famous things is that always invert. So if you know how you're going to die, you absolutely want to avoid that. So that's exactly what Neuroevolution does. So sponge a lot of individuals. If they die, just ruthlessly kill them and keep the fittest. I think this is a very cool idea.
Yeah, excellent. Well, what are some of the examples of these kind of successes that we've been able to achieve already in being creative and being agentic?
I think one thing that's very exciting is this era in Neuroevolution of open-endedness, where you have agents that not just follow one particular goal or want to achieve one particular goal, but you want to discover many kind of different behaviors in an open-ended way. And a lot of the focus on Neuroevolution in the past was on, okay, we have one objective that we want to get to, but the focus has changed. Now we want to discover like ideas like quality diversity. We want to discover like a whole array of different behaviors that solve the task in different ways. And I think that's very exciting. And that also makes it quite different to typically deep learning, machine learning approaches.
Yeah, I think building on that, I think the aspect of serendipitous discovery using evolution techniques, it's kind of like how nature discovered all of these wonderful things in our current world. Like nothing was really planned. And like this sort of discovery process is a bit more fundamental. And I think it actually is the core of scientific discovery. Most of the greatest scientific inventions are created in a serendipitous way. And actually, recently, one of the applications for evolutionary computing is actually combining it with modern machine learning or LLM agents. And I think right now we're seeing many applications of combining evolutionary approaches, open-ended discovery, and this leading to this new wave of AI-assisted scientific discovery approaches, which is really exciting.
Yeah, no, I just think one thing to add is like this really exciting area where this really shines is like the combination with generative AI and language models. And I think there's a lot of room where we can go beyond like next token prediction in giving these models more agency, but also like combining like the Sakana, the model merging, combining different models together.
Yeah, very topical. And it takes the generative AI one step further than it would go otherwise. I've been always just fascinated by the creativity. I mean, this was the funniest thing that you could do when you were a student. Your computer actually did something you did not program up. It learned it on its own. And this is on steroids with evolution. So, for instance, we discovered using neuroevolution approaches that basil doesn't need to sleep, right? That wants to have lights on 24 hours. This would not have happened. We built a cyber agriculture system and simulated it and came up with recipes automatically. And Neuroevolution came up with this strategy of how you actually tend to these plants. And we discovered that basil doesn't need to sleep. Lights on 24 hours. It survives and thrives. Another example is to use it to leverage human creativity. So we had a system where humans designed how to cope with the pandemic. What kind of non-pharmaceutical interventions should be there? Schools, buses, travel, workplaces, and masks, and so on. What do? Well, humans decide various policies. But then we used neuroevolution. We distilled those policies into neural nets, evolved that population, and discovered much better solutions. And what was even most fascinating was that there were DNA from the human solutions that ended up in these final solutions. From not so good human solutions. There was latent potential that was only realized when we brought in evolution, and it knew how to combine it and how to make it really work. And the third dimension, I think, is biology, that we have evolution and we have neural networks. So this is a very good approach to understanding what happens in biological evolution. For instance, how did this complex behavior of hyenas stealing a kill from much, much stronger animal, lion, how can that happen? They have to coordinate their attack precisely, time it. And this can be modeled using neuroevolution. We can identify that there are stepping stone behaviors like bold behaviors and reserved behaviors. And when you combine them just right, you can get something that's complex. So understanding biology as well using neuroevolution, I think, is an excellent direction. So these are all things that we've seen already, and they are very exciting. What do you think is going to happen in the future? Where's neuroevolution going?
I think one thing, I think people in the past always said, oh, neuroevolution is, you can't train like really big models with neuroevolution. But I think now we are seeing some evidence like from Cognizant and also other labs that you can actually train, you can directly evolve like really massive language model as well. So I think now is the time, now we can really scale up neuroevolution, like we can scale up the size of the models we can train, we can the population sizes we can train. Imagine training like population sizes of millions of individuals in really complex worlds. I think I'm really excited what kind of behaviors could fall out of that.
Well, I think when people are talking about AI in general, the AI ecosystem, there's a trend that people mean machine learning is AI, but I think evolutionary computing has always been an integral part of the AI ecosystem. In some sense, machine learning is kind of like the learning part, but the evolutionary algorithms is the outer loop of learning. Like, for example, even 10 years ago, or even longer than that, evolution has been used for optimizing neural network architectures so that neural networks can learn, but evolution defines what the architecture should be. More recently, agentic evolution is very common practice. So LLMs are used for training, like how these agents can talk to you or to generate text, but evolution defines how these agents behave in a collective way. And we're seeing the same thing in agents applied for scientific discovery. So the LLM agents may produce individual hallucinated ideas, but evolution will kind of like is the coordinator or the conductor behind the entire system of agents. And I really think this kind of combination of evolutionary architecture on top of learning algorithms is going to be key to reach very strong artificial intelligence in the future.
Yeah, I also think that neuroevolution, or say evolutionary algorithms as a whole, is a missing link between, say, static AI and the evolving AI. So right now, once we train those large language models or whatever systems, they stay static, right? But our environments, the environment that we're living in are constantly changing. And the changing and the chaotics are actually the key that enables us to be thriving here. And I think this applies to machine learning systems as well. And those machine learning systems, through evolution, either agentic systems or large language models, they should be adapting constantly to the environment, or say to the tasks they're dealing with. In this way, we might be expecting much more powerful AI instead of only hitting a lot of like benchmarks that are sort of cheating, right? AI systems always can hack those systems. So I think in general, we should apply neuroevolutionary algorithms to basically try to apply them to all the AI systems that we're developing, such that become more generally capable.
Yeah. And if you take a really big picture of thinking what the role of AI, machine learning, and neuroevolution in society might be, these are systems that discover decision strategies, behaviors. And we are in a position where if we could agree on what we want the society to be like. Do we want to have maximum productivity? Do we want to have equality? Do we want to care about the environment? What are the policies that we should enact so that we get to those goals? We can have an automatic discovery of decision strategies for business, for healthcare, for government and environmental protection, and then have Neuroevolution represent those, discover them and represent them. And this way build a society the way we like. It's a big picture, but I think this is, like I said, a missing piece. And now we have that. Now, everybody is working on transformers now, and they are working very well, but they're not very much like the brain in some aspects. Now, how do we come up with architectures that might do something like that, be more brain-like and perhaps continual learning and have metacognition? That's where we need a neuroevolution. It can come up with new architectures given these kinds of objectives and take the science of machine learning further.
Yeah, I think that's actually a good point. I think there's a lot of interest right now also in continual learning. And I think Neuroevolution is particularly well suited covering up with architectures that might be better at continual learning than current approaches are. Yep. And I think also scaling, you already mentioned that learning something about biology, but so far people have been doing this with very small kind of setups, right? And if you now imagine what could we learn if we can really simulate more cognitive architectures and larger population size, I think there's a lot of knowledge that can be gained too.
And you mentioned the large compute, and now we finally have environments, world models. David worked on world models, and now there's more world models coming out. We could actually put these neuroevolution systems into such models and ask very large questions. For instance, I'm really interested in how did language evolve? We could run a simulation where we manipulate the constraints and see what were the determinants for human language, actual grammar and structure. So very big biological questions and questions about intelligence could be asked now.
I think another trend in the future of AI development is how we scale this technology. I mean, scaling has played a key role in the success of AI, but what we're seeing is many developments of big monolithic AI systems. Now AI centers are built around nuclear reactors, for instance. But I think evolution is an alternative way for how we can scale this technology. It may enable more modular systems, collaboration between millions of different models, as opposed to a single monolithic model, like reflecting how our own human evolution acts. So I think that's very promising.
Yeah, I think that with the rise of those foundation models right now, robotics is taking off again, right? So for robotics, a traditional topic is that how do we design the morphology of a robotics? For example, for a collapsed mind, maybe we don't need a dog-shaped robot. Maybe we need a snake-shaped robot with some magnetics on its bodies, such that it would allow it to pass through all those trashes in this mind, right? I think that evolutionary algorithms would allow us to better not only evolve the morphology of the robot, but also maybe at the same time, as David mentioned, also changes its controlling mind, right? The neural network itself. So this co-evolution of the body and the brain itself maybe lead to some more exciting discovery in the society of robotics. That's my personal take.
So why did we write this book? Why is this a good time to actually put everything together and provide this for the rest of the world?
Why did we write this book? Well, I think 3-4 years ago, Sebastian and Risto pinged me, emailed us and say, "Hey, we should write a book on neuroevolution." And that's why it's here. But really, I think when I was learning about neuroevolution more than 10 years ago, I was reading many of Risto's papers, Sebastian's papers, Ken's papers, and things were all over the place. And I think, when we want to learn about a certain subject, I think it's a good idea to have many concepts in the same place so that people can kind of have a reference manual. But at the same time, we also wanted to have a book that builds a community and grows together. So I think this was one of the goals of this endeavor.
Yeah, for me, I have more of an industry background. So during my work at Google DeepMind and Google Brain, I find that people are constantly focusing on gradient descent, using gradient descent to optimize everything. This works great, but I think a lack of a diversity, right? I also read a lot of the papers from Neuroevolution. I think this is a cool idea. Applying them to the same problem usually give you different answers and a different robustness. So I think this is great, and that's why we put a lot of related exercises, not applying only to those classical problems, but also to, say, large language models, right? To innovate those engineers or, say, researchers in the industry to be more engaged in applying neuroevolution to those new problems. So that's my personal incentive.
Yeah, and we came together because we all represented different aspects. I have a long history. I mean, I studied in the 90s, and you guys are very recent. You are part of it, in academia, others are in industry. Some are experts in reinforcement learning and then Gen AI. So we all represented different perspectives to this, and it turned out that there's a coherent body of knowledge that can be put together, and now we can actually teach courses based on it. And a person can pick up the book and be up to date. And that, I think, is a really lofty goal, but I think we achieved it.
And following up on this, I think it's also, we have these nice info boxes in the book, how we all got into neuroevolution, which, so if you read the book, you can, check those out. I think they're quite nice. And I think also what I want to say that it's more than just a book. We also have this whole website that Yujin said, there are exercises, but there are demos on the webpage. There are many other resources, and we also have we want to build a community around it, a larger community. So we also have a GitHub where people can upload their own material or link their own web page. So we invite everybody to kind of join this endeavor, and there's a lot of resources that we put on this web page. There's the demos, there's the exercises, and we really want that everybody contributes and hopefully it inspires also the next generation of people this book. And let's work on it together.